Hi, welcome to the universe of first-order RL circuits. In this video, we will give you a practical and interesting example. The first response of a first-order RL circuit where there is a voltage source and a switch in series with a resistor and an inductor. The switch K is initially closed, ensuring that the voltage in the inductor UL is 0 and its current IL remains constant. The current in the inductor at time 0 is 0. At that instant, the switch K is opened and remains open from that moment on. We want to know what happens to the current and the voltage from that instant onwards, that is, for t equal or greater than 0. In here, you'll find math formulas, some illustrations, and graphs, so you can pause the video whenever you need a little bit more time to let the information sink in. But let's get into it. In a circuit with such initial conditions, we have a voltage U equals E for t equal or greater than 0. The differential equation that describes the behavior of the circuit is as follows. In case you want to remember how to get here, you can watch our introduction video to first-order RL circuits. Alright, knowing the value of U, which is E, we can replace it in this equation. Then, to determine the current on the inductor for t equal or greater than 0, we need to solve this first-order ordinary differential equation. First order because it only has the first derivative of one dependent variable, IL, with respect to an independent variable, t. In this equation, E, R, and L are constants, and IL is the unknown. The solution to this equation is the following expression. Be aware that this solution is obtained through the Laplace transform. We can also determine the voltage across the inductor for t equal or greater than 0, which is given by this equation. Well, but how do we get to it? It's easy actually, through the equations that we went through before. The voltage U is equal to the sum of the voltage UR across the terminals of the resistor with the voltage UL across the terminals of the inductor. Since U equals E for t equal or greater than 0, we can rewrite the expression in the following way. UL equals E minus UR. Knowing that the current through the resistor and the current through the inductor are the same, and remembering, of course, Ohm's law, we have IL equals UR divided by R, which can be rewritten like this. We can then replace UR in the expression UL equals E minus UR. Ultimately, by replacing IL with the equation we saw above, this one, we get our final expression, which is this one. Cutting things short, these are the equations that translate the force response of a first-order RL circuit. But now, let's analyze the graphic representations of these expressions. After a time equaling L divided by R, the current through the inductor with an initial value of 0 reaches 63.2% of the value of E divided by R. This time period, L divided by R, is called time constant, which is represented by the letter tau. After 3 times that time, that is, after 3 times tau, the current in the inductor reaches 95% of E divided by R, and after 5 times tau, it reaches 99.3% of E divided by R. On the other hand, the voltage UL across the inductor behaves in the following way. For the instant t equals tau, the voltage UL reaches 36.8% of its initial value E. At the instant t equals 3 times tau, UL reaches 4.9% of its initial value. And at the instant t equals 5 times tau, UL reaches 0.7% of its initial value. In conclusion, we can see that the initial value of IL of 0 equals 0 and the initial value of UL of 0 equals E. We can also see that as t tends to infinity, the current in the inductor IL approaches its steady state, which is E divided by R. And also that as t tends to infinity, the voltage in the inductor UL approaches its steady state, which is 0, showing that UL only has transient state. But let's take a look at another situation. If the switch K is open at an instant t equal to t0 instead of at time 0, we use the same line of thought with only a few twitches. The current on the inductor will be defined by this expression, and the voltage across the inductor by this one. Therefore, the graphs obtained will be the following, where it is shown that the current in the inductor begins to exist only from the moment t0 instead of at time 0. In the next video, we'll present you the total response of a first-order RL circuit, so stay tuned. See ya!